It's a great pleasure to be back at Harvard. I haven't been here for a very surprisingly long time. And it's a particular pleasure to speak in this conference in honor of John Tate. I never really interacted scientifically with John, although, of course, his work permeates everything in our subject. But when I moved to Harvard and started a family, he and Carol were extremely supportive and kind, and I'm very grateful for that. So what I want to do this morning is start off by reminding you about the Tate-Nakayama theory of the cohomology of tori over number fields or local fields, explain how that was taken forward by Bob Kottwitz, one of John's students, and then at the end say just a word about one use of this theory. So in the 1950s, Tate and a number of people, including Tate, Nakayama, and Vey, discovered the fundamental class in the Galois cohomology of either local or global fields, and the associated Vey group. And for instance, Tate used it to reconstruct the Artin reciprocity map. And so the first thing I'm going to do is discuss how to use it to calculate the cohomology of tori. So let's start in the local setting. So let E over F be a finite extension of local fields, p-adic fields to be precise. And let me give myself a torus over the smaller field, which is split by the larger field. And of course, to give yourself a torus is the same as to give yourself a finite free abelian group with the action of a Galois group. If I've got a torus, I can look at its co-character group, just the set of homomorphisms from GM to the torus over suitable, well, over E in this case will do. So it's, as I say, a free abelian group of rank equal to the dimension of the torus, and it comes with a natural action of the Galois group of E over F, and given this data, you can reconstruct the torus. And then the question that Tate and Nakayama answered was how to use knowledge of this co-character lattice to calculate the cohomology of the torus. Well, the answer is best expressed in terms of Tate cohomology, which was mentioned yesterday. So Tate cohomology is a way of splicing together the cohomology and homology of a finite group into one cohomology theory indexed not by the positive integers, but by all the integers. So in a positive degree, the Tate cohomology just equals the cohomology. In degrees less than -1, the Tate cohomology equals the homology. And in degrees 0 and -1, you get, respectively, a slight modification of the usual zeroth cohomology or zeroth homology described by the exact sequence at the bottom of that screen. So, as I say, class field theory, they knew that class field theory gave them the so-called fundamental class in H2 of the Galois group, acting on the multiplicative group of the field. And what they proved was that if you take the cut products work in Tate cohomology. If you take the cut product with the fundamental class, that gives you a map from Tate cohomology in degree I, with coefficients in the co-character lattice, to cohomology in degree, Tate cohomology in degree I plus 2 of the Galois group, well, I guess naturally with coefficients in the co-character group tensor over Z with the multiplicative group of the field, but that's nothing else than the E points of the torus. So that's the answer they gave. So for instance, if I take the torus to be just the multiplicative group for a moment, then in degree, if I take I equals -2, on the left-hand side, well, the co-character group is just Z with the trivial Galois action. So on the left-hand side, Tate H-2 is just the first homology. So I get the first homology of the Galois group of E over F with coefficients in Z, which is just the abelianized Galois group. And on the other side, I get Tate H0, which, if you remember the definition, the previous slide, was the invariance, the Galois invariance of E cross, which is F cross, modulo the image of the trace, which in this multiplicative case is the image of the norm map. So the Tate-Nakayama theorem specializes to an isomorphism between the abelianized Galois group and the multiplicative group of the field F modulo the norms, which is, of course, just the inverse of the Artin reciprocity map. Or I could take I equals 0. In this case, H0, well, the invariance of Z is Z, modulo the image of the trace map. Well, that's just multiplication by E over F, so I get Z modulo the degree of the extension. Goes isomorphically to an H2, which is just the Brouwer group. So I cover the usual description of the Brouwer group. The fundamental class, of course, being a class in H2, has another interpretation. H2 describes extensions of the Galois group by whatever I'm taking cohomology of. So this fundamental class in H2 parameterizes an extension of the Galois group of E over F by E cross. Just from cohomology, we don't get it completely canonically. It's unique up to isomorphism, but not unique isomorphism. The isomorphism can naively be composed with conjugation by anything in E cross. However, in this case, we do have a completely canonical description of it, at least if I give myself an algebraic, if I'm working within a fixed algebraic closure of F. I can take the Galois group of the maximal abelian extension of E over F and take those elements of that Galois group that, when I restrict to the maximal unramified extension, are an actual integer power of Frobenius rather than a limit of integer powers of Frobenius. So in this case, it's completely canonical. So Kottwitz suggested replacing the cohomology of the finite group, the Galois group of E over F, by the cohomology of the Weil group. And he suggested not taking the whole of the cohomology of the Weil group of the maximal abelian extension of E over F. And he suggested not taking the whole cohomology, but simply the part of the cohomology given by cocycles whose restriction to E cross, sitting inside the Weil group of E ab over F, come from an algebraic map of tori from Gm to T, so an element of the co-character lattice of T. And co-boundaries are exactly the same thing. So we get what people call the algebraic cohomology of the Weil group of the abelianization of E over F with coefficients in T, and it's a strictly bigger thing than the whole of the Galois cohomology. And then we can see if we can understand this. Now, does this work? Oops, disaster. Yeah, so on the left here, I've written the Nakayama-Tate isomorphism between H-1 Tate cohomology and H1 Tate cohomology, which is just H1, from the co-character group of the torus to the E points of the torus. So this is the Nakayama-Tate isomorphism. The H-1, if you remember, is the Galois invariance, and you take the trace zero part. And that certainly sits inside the the Galois coinvariance. That certainly sits inside the whole Galois coinvariance. And then I've written this Kottwitz H1 algebraic here, which contained this. Now, there's a natural map here, because if I took E equals F, then all I need is the action of E cross. So the H1 algebraic W E ab over E becomes just the co-character group. And then there's a natural co-restriction map from here down to the more general case, the cohomology of the Weil group of E ab over F. And certainly this Tate H minus 1 sits inside here. It looks as if these two maps are completely different, but what Kottwitz checked by an explicit co-cycle computation is that this little square on the left actually commutes. So this co-restriction map really extends the cut product with the fundamental class. And you can extend this diagram. The top row is just the four-term exact sequence defining H minus 1 Tate and H0 Tate of the co-character lattice. The bottom row is different in nature. It's the inflation restriction exact sequence for the Weil group of E ab over F and its quotient, the Galois group of E over F. But rather amazingly, Kottwitz checked that not only this commutes, but the whole diagram commutes. And the fact that the Tate-Nakayama theorem, that this is an isomorphism and this is an isomorphism, then implies that the co-restriction map in this case is an isomorphism between this new algebraic cohomology of the Weil group acting on the torus and the Galois coinvariance of the co-character lattice. Well, one advantage of Kottwitz thinking of things in these terms is that he could generalize this to any, well, the definition at least extends to any algebraic group over F. In fact, there are two natural generalizations, what people call the algebraic cohomology and the basic cohomology. So again, I take now non-abelian co-cycles valued of the Weil group of E ab over F, valued in the E points of F. And again, I'm going to require something about the restriction of them to the copy of E cross in the Weil group. Either they should just be given by a co-character from GM to the group G, or they should be given by a co-character in the basic case that's valued in the center of G. And again, co-boundaries are just what they usually are. Co-boundaries take these algebraic and basic co-cycles to themselves. And Kottwitz went on to show that the inverse of this co-restriction isomorphism in the case of tori, so in the case of tori we had maybe I should first tell you what the algebraic fundamental group of G is. If I have so now it's important that G is reductive. If to any reductive group, one can associate an abelian group, its algebraic fundamental group. It's defined, you just take any maximal torus in G, you take its co-character lattice, and you mod out by the sublattice generated by the co-roots. So this gives you, as I say, a finitely generated abelian group. It's completely canonical. It doesn't depend on the choice of maximal torus. Any two ways of conjugating one to another would induce the same map on the algebraic fundamental group. For a torus, the algebraic fundamental group is just the co-character lattice. So, so in the case of a torus, we had a map from here to here, in fact, an isomorphism from here to here. And what Kottwitz showed was that if we look at the inverse, there's the inverse of the co-restriction map, there's a unique way to extend it to all reductive groups. There's a unique way to extend it to all reductive groups that's functorial in the group G. And more than that, he showed that in this setting, if I restrict it to the basic cohomology, it actually gives an isomorphism. So you might ask, why did he do this? What's this good for? And I can't give a sort of completely pithy answer to that. I think it first arose in attempts to count or classify the points of Shimura varieties over finite fields. But my sort of vague feeling is that it seems to have two different functions. One is that group theoretically it's very convenient. For instance, if the center of G is connected, then inner forms of the group would normally be parameterized by the cohomology of the adjoint group, not the cohomology of the group itself. But in this setting, inner forms all arise from a basic Kottwitz cohomology class. And secondly, it seems to have something to do with algebraic geometry. For instance, H1 of GLN parameterizes rank n isocrystals. Sort of a final warning about this. I've started with a finite extension, as indeed Tate did. One might, of course, want to vary the finite extension. So one might want to replace the E by a bigger extension of S, say D. And then, of course, we have the natural restriction map, as we do for Galois theory, from this extension to this extension. But this is not compatible with Kottwitz cohomology, because somehow the norm map doesn't come from a map of tori. If one can, though, of course, there is a way of comparing the cohomology for different extensions, and if one tries to patch them all together, then one obtains some sort of cohomology theory for a different group, a group which is an extension of the Galois group of F bar over F by, well, the protorus, which is the protorus that has co-character group Q, the inverse limit over GM of the nth power maps for all n. So the F bar points are just some limit of F bar cross over all nth power maps. And this is an extension completely canonically associated to F bar and F. It has some relation to the Weil group. So this extension is certainly not split, but if you restrict it to the Weil group, then it does split. In fact, the splittings are parameterized by the choices of uniformizers in F. So it's slightly, this group looks much more like the Weil group of an Archimedean field than the usual Weil group in local class for local fields. Okay, so let me now turn to the global situation. So global class field theory, again, gives a fundamental class. If I have a finite extension of number fields, gives me a fundamental class in the Galois group of E over F, valued in the Idel class group. And again, Tate-Nakayama proved that if you cup, well, I'm not sure who first proved this, is you cup with the fundamental class, you get an isomorphism between the Tate cohomology of Z and the Tate cohomology 2 degrees higher in the Idel class group. And again, for instance, if you take I equals -2, you get the inverse of the Artin map. And again, this class gives some extension of the Galois group of E over F by the Idel class group. In this case, we don't have a completely canonical definition of this Weil group. Again, it's unique, but it's unique up to isomorphism that's itself only unique, composed with, well, in fact, you can get down to conjugation by something in the connected component of the identity in here. But you still have such an extension. However, we were interested in the cohomology of the E points of tori, and we're getting the Idel class group here, so we need to, this itself doesn't answer the question. And to describe the solution of Tate-Nakayama, I need a little bit more notation. So let me write VE for the set of places of the field E. Comes with a natural action of the Galois group of E over F, permuting the places. And then let me look at the free abelian group with bases the places of E, and the subgroup of those formal sums NV times V, such that the sum of the coefficients is 0. So, oops, yeah. Getting ahead of myself. So this is a subgroup in here with quotient group Z, of course. And then I'm going to consider the protorus, S, which I'll denote SE, over the field F, which has as its character group this group ZVE0. The free abelian group on VE, or the subgroup of the free abelian group where the sum of the coefficients is 0. And this comes with the natural action of Gal E over F just from the permutation action on the places. And then there's one more rather complicated object, maybe appearing at first sight, object I have to consider, which I've called E globe E over F0. I simply take the product of the Idels over one copy of the Idels for each place of E, but I take the subgroup of those things such that each component has the same image in the Idel class group. So the coset XW E cross is independent of W. So if you like, if I fix a place, it's one copy of the Idels and then something in E cross for every other place. Well, this group has relations to various other things we've just been considering. If I take the common image of any component here in the Idel class group, I get a well-defined map to the Idel class group, which is Galois invariant. I can, of course, project it onto any component W, so I get a map to the Idels, but this is only equivariant for the decomposition group at W. And if there's a diagonal copy of the Idels in here, if I mod out by that, I just get the E points of this Tate-Nakayama torus, SE. And now I want to consider the cohomology of these 4 objects. So we know in the cohomology of the Idel class group, we have the global canonical class. In the cohomology of the Idels, now just for the decomposition group at W, well, we have a map from the completion of E at W into the Idels, just embedding in the W place. And this is in Galois equivariant for the decomposition group. Here we have the local canonical class, so the local canonical class gives a class here. And what Tate and Nakayama proved was there's a unique class in this funny E-globe group, in the Galois cohomology of this funny E-globe group, that maps both to the global canonical class and the images of all the local canonical classes. And once we have this class, you can project it to the cohomology of SE, if you like. And then again, what Tate and Nakayama proved is if I take the Tate cohomology in degree I of the abelian group, which is homomorphisms from the torus SE to your general torus T, and you cup it with the canonical class, that's an element of H2 with coefficients in the E points of SE. Well, the cut product goes to HI plus 2 with the cohomology of the E points of T, and they prove that this map is again an isomorphism. And these homomorphisms can be rewritten as a tensor product of the co-characters of T times the characters of SE, if you like. Okay, so now we do have some sort of a relatively elementary description of the cohomology of the E points of the torus. If you're bored or lost, you can you can stop paying attention and try and specialize it to the case that T is the multiplicative group and I equals 0, and you'll recover the normal description. This is then H2 of E cross, and you should recover the normal description of the Brauer group of E over F. And just as in the other settings, if we have a class in H2, we get an extension, this time by the E points of this pro-torus SE, or the Gauer group by the E points of the torus SE. And again, we don't know this up to unique isomorphism, only up to only unique up to conjugation by an element of SE of E. And again, Kottwitz showed exactly the same procedure he had before, defines a new cohomology theory, this time the cohomology theory of this extension E over F, the extension of the Gauer group by the E points of the torus SE. We take those cohomology classes whose restriction to SE is just given by an algebraic homomorphism from the pro-torus SE to T. Co-boundaries are the same thing. And I haven't written out the whole diagram again, but the Tate-Nakayama isomorphism between H-1 Tate and H1 extends to the co-restriction isomorphism. This should not, no, this shouldn't be an isomorphism, but it at least extends to a map here. Sorry. Yeah, in this, yeah. If E splits T, I think this will be an isomorphism. And again, in exactly the same way, you can extend it to the cohomology of any algebraic group over F by taking non-abelian cocycles whose restriction to SE is either comes from an algebraic homomorphism from SE to G or from SE to the center of G, and you get algebraic and basic cohomology. And again, Kottwitz shows that the inverse of the co-restriction isomorphism I wrote down a minute ago gives maps from the algebraic cohomology of any reductive group G to, this time I get the character lattice of SE, namely these sums of integers times places with the sum of the coefficients being 0, tensored the algebraic fundamental group, and then take the Galois coinvariance of the whole thing. And the fact that we know what it is for tori, and its functorial in G defines it uniquely. This Kottwitz cohomology, this global Kottwitz cohomology comes with some other structure that I don't have time to explain in great detail. There's a localization map from the homology of E over F to the local algebraic homology of the Weil groups, as you might expect, though it's, again, slightly harder to define than you might naively have guessed. And in the local situation, we knew this map was an isomorphism. Well, maybe we need to take some limit over all E, and then this, in the global setting, this is again very close to being an isomorphism. The problem being that I described the local maps at a p-adic place. At infinity, things aren't quite as simple. The local map at infinity, which I didn't discuss, is not quite an isomorphism. So in the global picture, the the failure of this to be an isomorphism is exactly measured by the failure of the local maps at infinity to be an isomorphism. But if you give yourself a class here and local cohomology classes at infinity, at least if we're in the basic case, with the same image where they should have the same image, then you get a unique class here. So it gives very good, you can control this cohomology very precisely. Okay, so now let me change direction completely for a bit. I've discussed the Tate-Nakayama theory and its extensions by Kottwitz. And to talk about Shimura varieties for a moment. So, following Shimura's investigation of many different moduli spaces of abelian varieties with additional structure, Deligne proposed a theory of Shimura varieties. And to certain data, which he called Shimura data, he was going to associate algebraic varieties with certain properties. So Shimura data is a reductive algebraic group over the rational numbers, together with a real points of G conjugacy class, so not really a conjugacy class of co-characters, but a real points of G conjugacy class of co-characters of G, defined over C themselves with three properties. The first being that if you take the product of the co-character mu with its complex conjugate, then it's valued in the center of G. Once it's followed, taking products of co-characters is not always a good idea, but if the product happens to be valued in the center, then it is again a co-character. The image of -1 under any of these co-characters in the adjoint group should be a Cartan involution, meaning that if I take the inner form of the adjoint group gotten by composing complex conjugation by this element mu of -1, I get a compact group. And finally, mu should be minuscule, meaning that if I look at its weights in the adjoint representation, I get just 3 eigenvalues. Two such data, and maybe a sufficiently small open compact subgroup of the adelic points, finite adelic points of G, there's a unique smooth quasi-projective variety over the complex numbers, which is characterized by a description of its complex points as a complex manifold. So I should have said that in this situation, the set X naturally gets a structure of a complex manifold. You can describe, say, explicitly in terms of mu what the action of the complex numbers on the tangent space of X at mu should be. So this gets a unique structure. So this is uniquely a complex manifold. This is a discrete set. If I take the quotient of G, so GA infinity mod U is a discrete set, X is a complex manifold, I take their product, GQ acts on the left on both of these, on X by conjugation and on the finite adelic points of G by translation. And so this is this becomes a complex manifold. In fact, it's a finite union of quotients of X by discrete subgroups of the GQ. And it's a theorem of Bailey and Borel that this is a quasi-projective variety, and it's a theorem of Borel that it's uniquely so. And these varieties are important. One reason they're important is that they're highly symmetric, not in the sense that they have many automorphisms, but if I take the tower of all of them, as U varies, it has a huge number of automorphisms. Or put another way, each of these things has a lot of self-correspondences. So that's one way in which they're special. Another way in which they're special is that they can be uniquely defined over number fields. Or more precisely, you could ask, given one of these things and an algebraic automorphism of C, just as a field, you can take the conjugate variety and ask, what is it? And Langlands suggested it should be again one of these Shimura varieties. And not only should it be a Shimura variety, but it should be a Shimura variety with he gave a recipe for the group and the conjugacy class of co-characters, which should give rise to the conjugate Shimura variety. Unfortunately, the recipe relies on auxiliary choices. You need a lift of the automorphism of the complex numbers to something called the Tate-Nakayama group, or the rational points of the Tate-Nakayama group. And you need to choose a special element of the X, the set of this set of co-characters, with the property that mu factors through a maximal torus of G defined over Q, not just over C. But given this auxiliary data, Langlands gave a recipe for a new group G and a new conjugacy class X. And for that matter, he identified the finite Gödelic points of this new G with the finite Gödelic points of the old G, and so we can send to an open compact subgroup U, we can get a new one for the new group. And he conjectured that there was an isomorphism between this the conjugate of the old Shimura variety and this new Shimura variety. And he also explained how it should depend on the auxiliary choices. So given two choices of alpha and mu, another alpha prime, mu prime, then he writes down a particular isomorphism between the two possible right-hand sides that makes the obvious triangle commute. But the recipe is, to my mind, absolutely horrific. It's a series of, he writes down very explicit co-cycles seeming to make arbitrary choices a number of times, and the only place this is all written down is, I believe, is in his Einmärchen paper. But anyway, he made a very precise conjecture. And this was proved by Borovoy and Jim Milne, another of, who's here, another of John's students. It's Borovoy. That you might not recognize, but I believe it's Jim Milne, near the summit of Everest. You can't see his face. And one consequence of this is that these Shimura varieties are always defined over number fields. In fact, a very particular number field, the field of definition of the geometric conjugacy class generated by X. So there were things that have long bothered me about this story. The sort of second one, but I've written it first, is that the dependence on this auxiliary choices and the very explicit co-cycles that come in and choices that come in Langlands' conjectures seemed sort of particularly complicated and messy. I felt there should be something more natural. And secondly, this data of Deligne, this G and X, parameterizes not simply the Shimura variety over this number field over which it's naturally defined called the reflex field, but it really parameterizes the Shimura variety over the reflex field together with a preferred choice of embedding of the reflex field into the complex numbers. And it's not really, I feel, what one wants to do. One wants to parameterize a variety over a field, and one doesn't really care about the choice of embedding into the complex numbers. So let me give an example of this, which has long been known. Let me take a non-Galois cubic totally real field. Of course, it has three infinite places, infinity 1, infinity 2, infinity 3, corresponding to three embeddings, Tor 1, Tor 2, Tor 3, of the totally real field L into the complex numbers. And there are three quaternion algebras with center L ramified at exactly two of the infinite places. So I'll write di for the quaternion algebra that's ramified at the two infinite places other than infinity I. And then there's an algebraic group over Q, defined by the fact that its Q points is just the multiplicative group di cross. And these are genuinely non-isomorphic as algebraic groups, or even its rational points are non-isomorphic as abstract groups. And you can extend GI, you can add some obvious conjugacy class of co-characters. I've written down one element of the conjugacy class. If I take the C points of GI, I get one copy of GL2C and two copies, well, there will be GL2C, but they're the Hamiltonian quaternions tensor C cross more naturally, and I just have a character at this one place. So this is genuinely different Shimura datum. They each give Shimura varieties over C, and in fact, the reflex field of GI-XI is the image of this cubic real field under the choice of embedding Tor I into the complex numbers. However, there's one variety over the field L which, under the embedding Tor I, gives the Shimura variety associated to GI and XI. So we've got really one variety, or collection of varieties, living over the totally real field L, but we've got completely different names for it, depending how I choose to consider L inside the complex numbers. And as I say, this doesn't seem satisfactory to me. My feeling was you should want to parameterize a variety over L, and you really don't, unless you want to do complex uniformization, you really don't care about the choice of embedding. Okay, so I will finish by discussing a suggested reformulation of this, which seems to me to sort of look more natural. So this is joint work with Jack Sempliner. I should stress that it's really, all the hard work is in the original Langlands theory. This is simply another way of describing the results. So we suggest that, first of all, I have to fix these various extensions of the Galois group coming from the fundamental class that we discussed in the first half of this talk. It's the local ones were canonical, but the global ones are not canonical. You have to make some choice of extension, and you have to also make choices of how you compare the local and global theory, which I'm going to sort of brush under the carpet, but you have to make such choices. And then once you've made such choices of these extension groups, what we propose is that if I'm given a field of characteristic 0, then rational Shimura datum over the field L should be a 4-tuple of the following sort. So again, G should be a reductive algebraic group over the rational numbers. It's less of a central role here. It turns out, as I'll say briefly in a minute, that it's really just a placeholder for a set of, well, at least if the center of G is connected, a set of inner forms. So we're not really choosing G, but G in all its inner forms. Psi should be a collection of basic Kottwitz cohomology classes at all places. maybe with some restriction that it's sort of unramified at all but finitely many, but some sort of restricted product of these local Kottwitz classes, with the property that the one at infinity, the component at infinity, if I take the inner form of G associated to that, then modulo center, it should be a compact group. This is typically what people might call incoherent. It typically wouldn't come from any global Kottwitz cohomology class. And then C should now be a geometric conjugacy class, not a GR conjugacy class or anything like that, but a geometric conjugacy class of the group G defined over the field L. It should consist of minuscule co-characters again, and there should be some relation between the conjugacy class and the co-cycle chosen here, that the sum of the Kottwitz coinvariants in the Galois coinvariance, the sum of the Kottwitz invariants of the local psi v in the coinvariance of the algebraic fundamental group should equal the image of C. Any element of C gives an element here, and in fact, every element of C gives the same element here. And then finally, U should be an open compact subgroup, in this case, not of G of the adels, finite adels, but of the inner form of G determined by psi over the adels. So it determines an inner form not over Q, but over the adels. And then to this data, one can associate a quasi-projective variety over the field L. In fact, it's a finite union of Deligne-Shimura varieties. In fact, isomorphic Deligne-Shimura varieties, but it's important to have a finite union. And that's maybe not a surprise. When people analyze Shimura varieties, they usually do so, or their reductions, they usually do so by comparing them to some sort of moduli space of abelian varieties with additional structure. And when you look at those moduli spaces, you don't get a single Shimura variety, you get a finite union of Shimura varieties. But these things will give exactly those moduli spaces will be one of these varieties. As we allow U to vary, we get an action of the adelic points of psi of G, finite adelic points of psi of G, as one might expect. In fact, one gets the action of a slightly bigger group that I don't have time to define that has the property that it permutes transitively the constituent Deligne-Shimura varieties. Now the dependence on the field and automorphisms of fields is completely clear. If you take a map of fields, sigma from L to L primed, then sigma of the Shimura variety to G is simply, you apply sigma to the only part of this data that's defined over L, namely the geometric conjugacy class, and you take the corresponding one here. No necessity to choose any additional data to define this. I said that it doesn't really depend on G. It only depends on the inner form of G. So if I replace G by at least an extended, or take at least an extended pure inner form of G, any inner form if the center of G is connected, then I just get the same Shimura variety, but I translate psi by the localizations of the co-cycle that gives the inner form of G. And it really, in a sense, it only depends on psi, the cohomology class of psi, not psi as a co-cycle. If I replace psi by the change by a co-boundary, so G in the E-adelic points of G, then I get isomorphic Shimura varieties, but the isomorphism is not completely canonical. It depends on the particular, more than one G might take psi to G of psi, and the map between them depends on the particular choice G, which is why I really needed here the co-cycle, not the cohomology class. And everything's functorial in G. Oops. Well, let me finish by going back to the example I had a minute ago. What happens if I take my non-Galois cubic extension of Q and take this example coming from different quaternion algebras? Well, let me write L tilde for the normal closure of L. Then those Shimura varieties, which all gave the same variety over L but with different embeddings, would have rational Shimura datum, what I've written here. The first thing, it only matters up to inner form, so let me just take the restriction of scalars from L to Q of GL2. And then I need a co-cycle, which I'll write down in a minute. Let me take it trivial away from infinity, because these quaternion algebras were only ramified at infinity. And a class I'll write down in a moment over the at infinity. Some open compact subgroup, and then some geometric conjugacy class of co-characters. Well, which co-characters do I take? The conjugacy class should be defined over L, so let me look for co-characters over L. This group, base change to L, becomes a copy of GL2 over L times a copy of the restriction of scalars from the normal closure of L to L of GL2. And I take the co-cycle, which is diagonal on the GL2 copy and trivial at the restriction of scalars. And for completion, I wrote down this psi infinity. It should be a co-character of the Weil group of C over R, which is C cross and J with the usual relations. And I just send Z to scalars and J to this triple of matrices in the C points of this, which is GL2 cubed. Okay, and I'll stop there.